Good afternoon, everyone. Thank you for being here with me today. I'm Xiao from the University of Oxford Department of Materials, and today I'll be discussing my research on a short fatigue crack in single crystal nickel. And this presentation will show how the use of high-resolution Ebsd technique can help us quantify the crack driving force and improve our understanding of how these fatigue cracks grow, offering new methods and perspectives to study these crack behaviors in situ. To begin with, I'd like to give a brief overview of the research background. In fatigue studies, we often use stress intensity factor range delta K as a primary driving force in Parse law to predict fatigue life. Empirical equations to calculate the stress intensity factor range delta K often rely on global conditions such as remote loading, sample geometry, and total crack length. However, this gets tricky with short fatigue cracks because these cracks are known to behave differently with long cracks behavior. And due to they interact with their surrounding microstructure. And this phenomenon has been discussed by many speakers at this conference. And it was first reported by some early researchers in 1980s. As you can see in this figure, the short crack, the growth rates of short fatigue cracks varies significantly from the long crack data. And these images taken from my colleague's publication display a short fatigue crack in Zircaloy 4. You can clearly see the shifts in their paths, demonstrating their interaction with the surrounding microstructure. So the empirical equations often fail to consider these crystallographic features, which leads to inaccuracies in our understanding. So to address this issue, we turn to full-field techniques with high spatial resolution. And one critical issue is how to deal with the full-field data effectively. Some researchers have used the field fitting approach. However, relying solely on theoretical solutions has limitations. For example, it can be very difficult to accurately define the crack tip position in the field of view. And also, it's very challenging to account for mixed mode loading scenarios, especially when the crack is inclined in the field of view. And so we proposed an alternative approach, which is the direct evaluation of elastic J integral. This method is more robust. We run finite element analysis based on full field data, and it provides a solid foundation for fatigue life prediction. This slide illustrates the workflow of our method. We configure a finite element model based on full field data. So we create a grid that mirrors the full field data. And then we identify the crack location, and the crack is inserted in the mesh. This step was followed by remeshing or adjusting the area in the crack vicinity, and all the data points obtained by full field techniques can be injected as boundary conditions in the model. We can deal with two different types of data. We can deal with displacement field from digital image correlation, and we can work with stream field data from Ebsd measurements. And the stream field data will be interpreted into a displacement field before using it. After defining the material properties, we run finite element analysis, and by assuming linear anisotropic elasticity, we can extract both mode 1 and mode 2 stress intensity factors and the J integral values from our calculation. So now the method is established. The objective of this research is to observe the short fatigue crack field in situ. To achieve that, we need to load a small specimen directly in an SEM, and it's ideal to exclude other influencing factors. It's ideal that the crack exists in a single crystal, and it should be a stage 1 short fatigue crack demonstrating interesting crystallographic properties. So now I'll discuss how to prepare the sample and testing it. The sample preparation and fatigue crack initiation was done by Robin Scales and Dr. Jichen, and I'll give a brief introduction. The shape of the sample was designed for perfect inertia during actuation, and each specimen was attached to this ultrasonic actuator. It can provide vibrations at 20 kilohertz. So as the specimen moves, the hammerhead lags behind, which causes the neck region to bend repeatedly during vibration at 20 kilohertz. So a laser system was directed on the sample surface, and a camera monitors the movement of the laser spot. By analyzing the span of the laser spot, the fatigue crack can be detected as soon as they initiate and change the compliance of the sample. So this is a powerful method to generate the small samples for mechanical testing. So the next question is how to load the sample in an SEM. So I designed this special test jig that features these two extruding rods that pull on the sample. So we can replicate the loading conditions on the sample surface. All the key parameters used during for the loading are listed here. The fatigue crack is approximately 230 microns in length, and we loaded the sample in 4 steps, with each load step 0.25 newtons. The next slide illustrates the inside view of the SEM vacuum chamber. The special test jig was mounted onto this special tilted loading stage, and this facilitates the in situ Ebsd test measurements. So the electrons emitted from the gun hit the sample surface, and they interact with the atoms in the sample, get diffracted, and form Kikuchi patterns on the Ebsd detector. So on the next slide, you will see a GIF that demonstrating the loading process between 0.75 newtons and 1 newton. The Ebsd scan area is marked on images, and it's focusing on a small area at the crack tip. All the key parameters for pattern acquisition are listed here, and all the raw images are processed using the procedures listed on the right-hand side. And the key information here is to reduce the noise and perform cross-correlation between patterns and the zero-strain reference in Fourier domain. The zero-strain reference point is selected at a location that's remote from the crack and with the zero load applied. The calculation is based on the assumption that there's no traction perpendicular to the sample surface. So this slide illustrates the elastic string tensor maps obtained by our calculation. As you can see, as the applied load increases, the magnitude of the string field data also increases with localized string concentrations occurring close to the crack. You may have noticed some strange rectangular features in some of the plots. These were caused by the damage on the sample surface. This damage can significantly affect the Z-related strings, but has a negligible effect on the 2D analysis. To simplify the finite element post-processing, the string field data were cropped and rotated to align the crack horizontally. And this is a typical size of the area that used for finite element post-processing. The contour definition are illustrated using these two plots. So the energy contours is centered at the crack tip with each, and as the contour number increases, with each additional layer of elements it contains. For example, contour number 1 surrounds the immediate crack tip, and the contour number 2 include another layer of elements outside of that. This is contour number 5, which contains 5 layers, and this is contour number 15. On the right, the final cropped string field data and the integrated displacement field data are displayed here. And for comparison, the theoretical field, the theoretical string field and displacement field were also plotted here to help us understand the connections between the string field and displacement field. These are the J integral and both mode 1 and mode 2 stress intensity factor results we obtained from our calculation. Each plot represents a single load step from 0.25 Newton to 1 Newton. In the initial load steps, as the variation in K values and J values across different contours are minimal, as the applied load increases, we could say the fluctuations become more significant, but it remains consistent, and the energy integral values are not sensitive to the paths as the contours expand. We calculated the mean, the average and the standard error from the data to represent the J and K values for each load step. Outliers were excluded from our calculation, which significantly exclude the data points close to the crack tip, where the measurements can be less reliable. To get an estimation of the theoretical J integral value and K values, we created a finite element model in Abacus. And we applied a 1 Newton load to the hammerhead to match the remote boundary conditions. And the comparison between local measurements and remote boundary conditions is detailed in these two plots. For mode 1 stress intensity factors, the Ebsd results is slightly higher. This is likely due to the possible bending from misalignment in the loading jig, and the surface stresses were increased as a result. Nevertheless, from mode 1 stress intensity factor results, we can find that the high resolution Ebsd method can provide us a reasonable measurement of the local elastic strain field ahead of crack tip. And interestingly, unlike mode 1 stress intensity factors, mode 2 stress intensity factors, it has limitations. So it doesn't increase with the load. It saturates in subsequent load steps. And this is possibly due to the local plastic deformation ahead of the crack tip, and the stress is relaxed here. So this means our measurements, our method measures the actual strain field, elastic strain field which is critical to the fatigue crack propagation, because this plastic deformation is critical to fatigue crack propagation. As an additional note, we also did J-integral analysis with the DIC obtained data, and you can see a sharp rise in the DIC results, which further confirms the plastic deformation happening ahead of the crack tip. And this was further confirmed by the JND analysis. We plotted the JND density ahead of the crack tip, and from step 3, we could see a clear increase in the JND density. And also by trace analysis, we further confirm that the propagation of crack plane aligns with slip variant that has a Harris-Schmidt factor. So I would like to thank you for your attention, and I would like to highlight these 4 important points. Thank you.
Thank you.